Excellent. So thanks, Yoshua. I'm going to talk about a line of research that me and colleagues at Google and actually also around the research community have been playing with, which is this idea of using recurrent neural networks to map onto sequences. The title actually originally was as language decoders, but as you'll see, we've kind of gone beyond language into some more creative ways of treating sequences as our output domain. But first of all, before I start giving you some of the background necessary, it is important to mention that this work, of course, has been done with a lot of great collaborators. And as I said, a lot of the papers are actually also from other groups and so on. So cheers to them. And so it is this is a deep learning workshop, I guess. So it would be interesting perhaps to try to answer the question, why is deep learning so popular now? I'm going to be a little more modest and try to tell you why I like deep learning and what the way I see kind of to be like sort of a deep learning promise is this fact that sort of deep learning allows you to do kind of rapid progress on many fields where data modalities can be very diverse without knowing too much about the domain. And I've been testing this idea myself to the extreme of actually going into a task where I actually don't know at all like how people solved it algorithmically, and really then treating it as a sort of data-driven approach with the models that I'm going to talk about here. So that really, of course, it makes them very popular because then it lowers barriers of entry of fields and so on. So I think that's one of the key why these workshops are so full, and it's become like quite a popular topic of research in machine learning. But let me first start with the basics, ingredients of the models that we worked on. First of all, let's just review some of the basics of language modeling. So here I show you just basically you could train a model, and a model here would be, I think this. Let's see. Yeah. So here, the model is just this box for now. And all I'm trying to do is put some probability distribution of the next word given a previous word, so from am to from. So this would be sort of a bigram model, and you can train many models to try to do that on some large data set. Of course, there's a lot of assumptions behind this model. You can sort of still, in a disconnect way, try to optimize this for basically a very large corpus of pairs of words. But of course, what we really want and what makes this picture more complete is to actually optimize the joint probability of sequences, or in this case, sentences. And in fact, a lot of the early successes of recurrent nets for discrete data was, of course, for language modeling. So essentially, I mean, here I'm just showing you some numbers on a large data set of news benchmark, but essentially, like you get very like nice perplexity improvements by using like large recurrent neural nets trained to basically just predict the word, let's say Barcelona, given not only from but all previous history. And this is very important that we condition on all the history in the past, and we don't do any approximations whatsoever. So this is sort of a nice model that makes no Markovian assumptions, if you will, another key ingredient of the success, especially for the more advanced models, is what I show here on the right. So I'm going to talk about LSTMs just implicitly in the whole talk, but I'm going to actually give you a single slide of kind of trying to give you a little bit of intuition why I believe this sort of special kind of RNN, recurrent neural net, that's called LSTM works. And this, as usual in deep learning, this actually has been around for a while. So the original LSTM was proposed in 1997, and for me what the key ingredient is came a little bit later in 1999, which is this forget gate. So let me try to explain you a little bit of the intuition why would we care about this forget gate at all. So let's imagine for a second that we're trying to predict the word Catalan given the word speak. So that already gives you a lot of constraints on what the next word is going to be. If you say some sentence like I speak, then it's obviously going to be a language coming next, but you might not know what the language is going to be. So to know that I speak Catalan, you need to, in this toy example, go back in the past where you saw, for example, the name Barcelona, and then in Barcelona they speak Catalan or Spanish. So that gives you like a lot of constraints on what the next word is going to be. But this connection can be very far apart in terms of number of words. So for example, here imagine there's many things that have been said between this Barcelona and the actual speak Catalan, right? So if you take just a simple recurrent neural net and you try to say, well, I want to establish a connection between Catalan and Barcelona, you actually have to realize that to produce this YT Catalan, given Barcelona that is very far in the past, you actually have to unroll this equation of a vanilla recurrent neural net, which essentially involves nonlinearity, let's say tan h, plus the times, and also like this matrix multiplication times WH over time. And that, as you can see, there's some problems there because you have a matrix that you keep multiplying by itself, sort of, and a nonlinearity that sort of is making like activation small. So learning these actually is very challenging, because you get all sorts of vanishing gradients and so on. So the LSTM, there's a bunch of equations and there's many variations that have been proposed, but the key ingredient there is that the state here, YT, there in blue, depends on, there's a bunch of nonlinearities and so on, but there is this previous state component-wise by this forget gate, okay? And so you basically add to your state the previous state times some number that is between 0 and 1. And, of course, this is more of a leap of faith, but actually some of the approaches try to make this forget gate very biased towards being just active all the time, i.e. 1. Then if you just write this equation now, you'll see that YT is just simply adding all the previous hidden states of the recurrent equation. And what that means is that in this case, YT is connected to this faraway input XT via just a simple nonlinearity and a matrix. So there's a shortcut for the gradients to flow, and that, of course, is, for this example, you could see why this would be more desirable. But this is very important, so especially for the sequence-to-sequence models, as you'll see in a second. And so let's dive in a little bit in this sort of paradigm. Again, there was like very little to be done to allow us to map not just simply model language, but map from an input structure, if you want, to an output structure. And actually, recently, there's been a lot of applications on all sorts of obvious problems and maybe not so obvious. One of the first successes was in machine translation. Then, of course, like captioning, as you've seen in this conference, a bunch of talks. Speech recognition, there's been some work being done, and it's hard to now fit everything in one slide, so I probably forgot something, so otherwise just imagine 8 and 9 and so on. But essentially, it's been applied, and there's a lot of papers in the last actually 2 years applying this principle. So what is sort of the main idea of sequence to sequence? How do you map a sequence onto a sequence? And if there is one slide that explains basically the whole talk, is this one. So remember, in language modeling, we looked mostly at the right-hand side here, where we were able to condition sort of generating some sequence up to Z given all the previous history. So all you have to do, very simply, is also input another sequence A, B, C, D, and that will allow you to exactly do a condition probability of the sequence output Y given X. And because of how the RNN works, what this is implementing is simply this chain rule product. So there's no approximations here a priori other than how you parameterize the model and how the information flows and the size of the layer. So of course there's a lot of assumptions, but in principle, this model really reads one word at a time, A, B, C, D, into its state, and then given that what it's read, it's trying to maximize the probability of the output sequence. Again, one word at a time, condition on what its output so far and also what the input was. And so in this framework, translation comes very naturally. And you can essentially map, for example, from English to French. That was one of the first language pairs that we looked at. And I mean, the surprising result for I think, like initially this was done both at Google and also at Montreal. It was very encouraging that we did not have any machine translation background, and we were quite easily we were able to match sort of the blue score, where higher is better, of kind of getting quite close, or say in between sort of the basic statistical machine translation systems and what was state of the art at the time. So in our first paper, we got like 35 blue score, which is somewhere between like 33 and 37, which was the state of the art at the time. And just remember that this baseline actually consists of a lot of research over many years and many groups of adding tricks very specific to the domain. So this was really, really encouraging, and the potential was very clear to the few of us who were thinking about this. And then, of course, a little more work by Thang, one of our interns, pushed this up, and actually also like work done at Lisa Lab. They actually participated in some competition for MT, and it also like they've won, I think, for the English to German translation pair. So this paradigm really was working on sort of a more classical NLP task. And these, I'm not going to read much into this, but just so that you get the idea on how this works. Really, you're reading one French sentence, word at a time into this state of an LSTM. And then what the thing produces is actually like just it's a fairly complex sentence, and generally it works fairly well as other more task-specific models. So this was great. This was like the motivating sort of start of this sequence-to-sequence model. And then for us it was, let's try to like be a little creative and think of the input sequence as something very special, which is actually not a sequence, just simply an image. So here the task is, you've probably seen this before, there's the task is for a human to describe this sentence, and you have a bunch of data with it, and then you produce sort of good, or by some definition of good, captions given an image. And really it's now very simple to think about this problem, and almost quite obvious. If we before knew how to put probability distribution of English words given French words, all we have to realize now is that, well, let's think of French as a special language, images as a special language that we condition on. And so the model is really almost like the translation model, where we take the image, we of course use some good ImageNet pre-trained convolutional net model to extract some sort of all we might care about the image, and then that is sort of used as the first special word that is not really a word. It's sort of, this is all I can see visually from the image, and then you optimally, you jointly train all these to optimize then the probability of the caption. So this was very natural, and it really just worked fairly well out of the box. But of course, a lot of groups started working on this. So when there is a competition, there are other things that we do to try to push the numbers up and so on. And a lot of these models are actually essentially the same underlying ideas. Some models are more, let's say, pipeline, where they have detection, and then they have some sort of way to generate a sentence. But some of these models certainly are based on recurrent neural nets and convolutional neural nets jointly trained. But there's still a large disparity of numbers here, right? So this is a little bit of what you don't see in many talks, even though some talks you see this, like it's sort of the ugly side of deep learning. So I've told you, you don't really need to know much about the domain. All you care about is setting the right objective function, throw it a bunch of data, and hopefully it will be statistically efficient enough so that you'll get like basically a pretty good mapping from your input to your output. But the reality is that when we submitted the paper, it was the best paper in terms of numbers, but then all these models kind of came very close to it. So then you start realizing there's other things, given the same model, the same parameters, the same code even to run the model, there are several tricks that will get you, that extra mile that will, give you like an edge on ImageNet, or in this case for this competition in particular. And that's sort of course, an unfortunate side effect that there's a lot of work to be done on tuning the model and so on. So here, my favorite single improvement. So by the way, like this is blue scored, right? So in NLP conferences, a blue score improvement of 2 or 3, sometimes they get like best paper awards, right? So this was just very silly things to do that kept improving our first system that we submitted to CVPR from 23 to the actual system I show you in that table, which tied with MSR and of course was behind humans, as one would hope. But there's like almost a 10 blue score improvement. And my favorite one here is all I did by accident, because beam search is a little expensive, so I tried to reduce this search procedure that you have to do at inference to find the optimal Y from 20 beam size to 1, and I saw that the actual, like all the numbers, all the metrics that they came up with for captioning were actually better. So that was like just, and I mean, the explanation behind this, it could be some sort of regularization effect, because if you are a little more inexact in your search, you might not overfit your answer so much to the model, and certainly there's lack of data and all these problems that we face every day in machine learning. But basically you can see that there is some pain to be had, and it's not as nice as one would hope. Nonetheless, the nice side effect is that once you train this, besides seeing an improvement on the numbers, we actually saw a clear improvement qualitatively on our captions. So remember, the initial model was a pretty good model. I mean, it was like doubling the blue score of the non-convolutional models at the time. But still, there's clear improvements on like more like image content. For example, here there is the exact same sentence from the previous one. This is not a typo. And you of course, once you train the models, you could kind of imagine, yeah, well, maybe this sort of thing, it thought it was a giraffe. I mean, we can always explain the failures, but really, just by doing these sort of very simple tricks on sort of the tuning phase, we got quite better. And this was not, it's not cherry-picked. I really took the first 20 examples of the validation set. And the improvement was quite substantial, basically on almost everything. And I mean, it was a reasonable guess for the initial model, but the best model really is more usable, I mean, if you care about products and so on. So it is really worth the time and the pain to like tune these models and sort of understand a little bit how to squeeze as much as you can from the model. And then actually there is some actually side effects there were like clear failures in some cases. Hot dog, sure, but there were actually nice things. For example, you start from a model pre-trained on ImageNet, and you use the last hidden layer as the kind of word embedding to inform the model that will generate language. But that model is trying to basically linearly separate all the 1,000 ImageNet classes, right? So if you don't fine-tune the image model, it is almost implausible that it will learn concepts like counting or colors. So one thing that we observed after saying, well, if we want a little better numbers, maybe we should eventually fine-tune all the convolutional net, is that the model improved from sort of not counting to counting, because probably it managed to surface these counting features up to the top layer, which is what eventually gets presented to the language model. So you can see many examples where the model was able to count, which is not an ImageNet class, so why would the initial model care about these? Or be a little more specific about colors. So here it knows that there's blue here, and this is also blue and yellow, which again are not specific ImageNet classes, even though certainly there must be some features in the lower layers that explain color. But you only get this if you're going to fine-tune your image model. So there was some understanding of what was going on, perhaps. And so that was like image captioning, and now we started getting a little creative on the kinds of things we map either from or onto. So this was, and I think this was the exemplar test of just try to make no assumptions whatsoever about how much I know about the domain. So I looked at parsing, which is something you hear about when you go to an NLP class, but it's a long time ago and so on. And so this was really testing like sort of this deep learning promise. And the way we thought about solving parsing was really, well, let's make it a supervised learning task and just go for it and try to train a model like the one I showed before. So in parsing, you input a sentence, John has a dog, and then the output, we try to do like constituency parse tree. The output is going to be some tree. And so the obvious thing that we tried to do, and that already worked, was let's linearize the tree. So instead of having a tree as an output, let's make it linear so that there is basically, I will give you instructions one at a time on how to construct the tree. And then you can rewrite this problem through John has a dog to this sort of funny language. It's still sort of a language that says open parentheses S, open NP, open NNP, and then backtrack, and so on. So we did sort of depth first traversal, and we did reprocess all the training set just to be of linear form. So then we could really just apply sort of the same model as in translation and as in captioning. to say, for example, well, read in the sentence and please produce the parse tree at the output, just by just optimizing again, like the the probability of the output sequence given the input sequence. So that kind of worked, but we needed some tricks of data augmentation and so on. And the reason is that in parsing, you don't get a lot of training data. So you are really, and in deep learning, I think in general, you're trading off a little bit of domain knowledge versus statistical efficiency, right? So if you have more data, let the data sort of figure out what is the right feature to extract from the raw form. Tara this morning was mentioning this. So certainly in parsing, we didn't have a lot of data, and in that scenario, we kind of had a model that was perhaps too weak to try to model parsing. So what we used is a form of attention mechanism that's been used again, like for some years for several, like Vision and Text Task. And the one we took exactly was the implementation by Badenau et al., which is sort of a pretty cool content-based attention. And just to describe a little bit how you modify this model to do that. So it seems kind of challenging to enforce all the information ABCD into the single vector, and then at the decoder time you say, hey, you just can use this, and I don't allow you to go back and see what the inputs actually were. So attention is sort of a nice way to allow you to say, well, I kind of know what I want to do, but maybe I want to make sure, and I want to go back to all the inputs, see them, and see how I can optimize for maximizing the output target. And so the attention mechanism, I'll explain a little more detail later, but essentially for each time step that you output, you generate sort of a query vector, and with this query vector, you sort of do some similarity between your query vector and all the inputs you've seen at the input side or the encoder side. And then you do a small neural network and a softmax, so then you get this attention mask. So this is between 0 and 1, and it's a scalar multiplying each of these input boxes. And then you just do a weighted sum. So you say, combine the input states with the attention that I think I should pay attention to given what I'm doing, and then bring these back to the decoder side and just concatenate the vectors and do a softmax. So the exact equations actually I'll show in a second. But then you can actually, one of the nice things of attention is also you can debug your model. You can see what did the model actually look for as it was decoding. Was it something useful or not? So here I'm going to quickly show how the tree at the decoder side is being generated, and this green arrow here will tell you where the model is pointing at on the input side. Okay? So let's see if we discover what, and remember all these weights are randomly initialized, not even the word vectors are initialized from anything. So these, like the data basically inform sort of what the neural net decided to implement. So what happens very deterministically so at Convergence is that as you generate the tree down, you keep your attention on the first word. And then as soon as you, for some reason, I mean, this is a pseudo explanation, for some reason, whenever it's generated the terminal node of the next word, then it moves the arrow to the right. So you can see this pattern. It moves, it moves, it moves, it moves. Then it goes back up. It keeps there. And then you generate now this guy, so it moves to the right and so on. And it does that exactly like that. And I'll show you the values of the attention. It is quite it's almost 1.0, even though this is a soft attention. And also what's kind of interesting is, well, once it's actually used the last one, what is it going to do now? And it actually, I mean, I'm not sure if this is general for every case, but of course you cannot inspect everything. But here, it decided to, as it was closing this branch, to move to here, which is the end of the left branch for this tree. And then it goes back. It says, okay, now I generate the period, which is always the last symbol in this corpus in particular, moves to attention at the beginning, and then you're done. That is pretty much deterministically. You always do period, close the sentence. And that was kind of amazing that it learned that just from the data. And as I said, these attention masks, these arrows, are actually quite sharp around where it's attending to. So here, you can see for each output you generate, the attention over the inputs, and perhaps the first time step, it doesn't matter, so it doesn't attend, but then pretty much deterministically, it moves this sort of pointer or stack decoder, or whatever it decided to implement. It keeps moving that, and then once it needs to close the tree, it goes here, and done. And we saw these sort of figures also for translation, where Badenau et al. They showed that it learns sort of alignments and so on. So this is sort of kind of cool. And besides being cool, more importantly, it really helped in terms of statistical efficiency. So here, I mean, there's lots of numbers, but the number that matters is that if you train with a very small training set, basically 40,000 sentence parse tree examples, so this is even smaller than MNIST, without attention and, with dropout and so on, you really did very bad on F-score. So F-score, the higher the better. And just by adding attention, you basically, and then of course adding ensembles and some other tricks, we were basically on par of like some reasonable parsers like the Berkeley parser and so on. And then the other trick we did in the paper was you can actually take a bunch of extra data that is not labeled, use a parser that is an existing parser with some agreement constraints to get extra training data, which we know neural nets like a lot. And then when we did that with this high confidence corpus, then the F-score improved substantially to the point that it actually is the best published number on this very classical Wall Street Journal Pentry Bank data set. And again, if you ask me about parsing, I really probably will not be able to answer much other than there's an input, there's an output, and you train a neural net. So again, and also, like, by the way, there's some side effects, like the speed of this thing is actually quite nice because it's ON with the size of, it's actually ON square with attention, with the size of the input. And it basically is as fast as some other parsers that were implemented in GPU. For technical reasons, we actually trained these on CPUs. So that was quite nice as well. And this is a slide I typically skip, so let's skip it. This is something I'm actually going to talk about tomorrow. That we have a poster, but you can also kind of map questions to answer in sort of conversational systems. And we train a model on a large corpus of open subtitles. So it's just essentially movies. And then you can see that the model kind of extracted some common sense things from just basically very noisy but very large data set. Again, I have no idea how to build bots and rules and so on. We actually compared these on Amazon Mechanical Turk on some subset of 200 questions and asked for people to say which one do you prefer, the neural one or the clever bot, which is some bot that some people designed some time ago. And it came ahead. I mean, take this with a grain of salt. I mean, it's very preliminary work, but actually there's some work already that has applied the translation principle to, for example, Twitter, to reply to Twitter and so on. So we hope that this is sort of a new data set that people could explore for sort of very unstructured, but nonetheless kind of like dialogue-like data. And then last, I want to talk about now, like, let's forget about language. Let's do something completely kind of strange or maybe not, right? Which is this standoff that we like to think maybe ultimately neural nets can write programs perhaps, or you can actually solve problems just by showing instances of the solutions, right? First though, let me tell you what the problem that the machine learning algorithm actually sees. So let's imagine there's a bunch of points on the plane, and I, as a human, I can tell you, hey, like, please find the convex hull of these points. And I could show you some examples, and you would get it eventually, and you could then find the convex hull either visually, or perhaps you can even write an algorithm to do this more or less efficiently. But if we want to translate this into machine learning, what we're really going to show the neural network or whatever other algorithms is going to be some sort of pairs of numbers, real numbers, that are sequentially ordered, but in this case you can see the order should not matter and does not matter in fact. And then we're asking it to output, let's say, some way to define a convex hull of 10 points. So here, you go from 2 to 4, from 4 to 3, 3 to 5, and so on, right? So this gives you what a convex hull is from a set of points. And of course, the tempting part now is, okay, well, I can generate a lot of training data, and we know how to map sequences to sequence, so why don't we just try that? And that's what we did in this paper. So again, the inputs here are going to be these. We just did two-dimensional points on the plane, P1 to Pn, and the output will be some sort of specification of the solution of whatever algorithm we might want to find a solution for. So again, you maximize these and input one point at a time and output this sort of special language. It turned out that this kind of worked, but as N grew, it wasn't that good. So what we end up doing, and what comes like in the last few slides, I'm going to show you how we actually were able to train a model only on 5 to 50 points for a convex hull, say, and then the thing actually generalized to find the convex hull quite successfully on like up to 500 points and probably beyond. So there were two things needed for this. First was attention. So attention really gave the algorithm, instead of linear time to read the inputs for each output, you kind of go back to the input. So it's kind of an O(n) square algorithm. And then, so these are actually the equations from the paper I mentioned. So that was addition number one. But still you have this annoying thing that the output is 1, 4, 2, 1. So now if I have a new point, it's sort of a new word that I've never seen. So how are you going to even map that to a probability, as you should, right? So if I see only up to 4 points, and I want to now output, I say I input 6 points, which I can do with a recurrent net, but how can I map 6 points to the output? Well, I don't know what these softmax weights should be, so I don't know the probability distribution here. So what we did, first we observed actually what the attention mechanism was doing. And not surprisingly, attention was actually focusing on the points that the network had to output one at a time already. So the connection there was very clear. Why can't we just simply say, instead of doing attention and doing a softmax back on the decoder, make the attention be the objective function and say, just point to the point and then maximize the log probability of the attention position to be the actual point that you want to output one at a time. So in this case, it would be just pointing to the first, the fourth, the second, the first, and then some special I'm done point. So now it is more clear, and this is sort of an instance of zero-shot learning also, if you will. We have 2 new points. We've never seen these points in training ever, but we can still sort of add them in the recurrent neural net, and then the attention mechanism goes to index, instead of 4 points, it indexes 6 points. So naturally, it can figure out, well, the convex hull actually uses 5 and 6, and this very simple sort of simplification of the attention mechanism, where we stopped at the attention and we did not bring back the information to some softmax in the decoder, actually worked quite well. So here are some numbers. Essentially, attention made the thing work, but it could not really be truly variable length. So the pointer network really was able to train it on 5 to 50, and you can see the area covered by the convex hull estimate is almost 100%. For even like when we extrapolated to 500. And then we were sort of being more like sort of trying to attack more general problems like triangulation. This is sort of Delaunay triangulations, which happen to be interesting for some reason. And our network can map the points to this set of triangles. It is mistaken sometimes. But it kind of, if you look from like the back, perhaps you don't see much of the difference of the actual Delaunay triangulation, which is a mathematical object, and then what the network output. Here I have a small video on how the network outputs one at a time these triangles, and the triangles are sets of 3 points. So the output sequence is really point, 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 end of triangle, point, 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 end of triangle. And then as it decodes, it basically keeps pointing to all the points one at a time, and so this is a very long sequence. And it makes mistakes for 50, but it kind of, it's pretty encouraging. And then the last thing we tried, let's see if this works. Maybe I have to click. So the last thing we tried is, well, let's go all out and let's try. All these algorithms have n log n solution. Let's try an algorithm for which to come up with an elegant and compact solution, I would have to like really use some non-trivial algorithm knowledge. And let's really give it just some instances of traveling salesman problem, which is NP hard. And then you can see the network actually kind of understood that it needs to traverse all the points and covering minimal distance and so on. So in this case, you see a mistake there on the top right. But then looking at the actual length of the pointer net versus the optimal length, whenever we were able to compute it in a reasonable time, was fairly close. And then we tested against 3 algorithms that are like just people. I mean, this is an important problem. So there's a bunch of algorithms doing TSP, as you can imagine. And the most kind of interesting for us result was that indeed it also extrapolated. So we trained from 5 to 20 cities, and then the total length for like, 25, 30, 40, it degenerates, right? This total length, it starts to be worse than even the worst algorithm that someone came up with. Nonetheless, it's for sure much better than just random guessing cities and visiting them. And it sort of gives this new, like, can we actually learn from just simply giving you data? The inputs are the points, the outputs is the sequence, and the answer is, well, partially, and we address some of the main challenges, which for sure are variable length and also give it some capacity through these attention mechanisms. And with that, I'm done. I'm happy to take some questions. Thanks for listening. Thank you.